5, Chapter 10, where we will be teaching you about angles! Hooray! Remember these from grade 4? Anyhow, Section 1 will be going over how to measure angles. Now I'm sure you're all familiar with, well, what is called a protractor. It's a tractor that's pro. Well, actually, no, it's not, but... So, you can use a protractor to find the measure of angles. Now, measure angle FGH. So this is the angle sign, so it's like this. And notice that G is the point that you are measuring. The point always goes in the middle of the 3 letters. Everything else, well, it doesn't really matter. It could be HGF or FGH. But the point must go in the middle. Or else you're going to be measuring a completely different point. And that would be bad because the teacher will look at it, go like, what is this child doing? And well, they're going to think that you are doing something wrong when you clearly understand what you are doing. Anyhow, so our first step is to place the whole of the protractor on the vertex of the angle, or the point. Now, the whole of the protractor is where the 90-degree line and the 0-degree line meets. Or you could call it the 180-degree line, but it's where it meets. It's not actually a hole in many protractors. Step 2, line up the 0 mark, or 0 degrees. The small circle means degrees. It's also the 180 degrees mark with one side of the angle. Step 3, find where the other side of the angle passes through the same scale. Read the measure of the scale. So when it means scale, it means the outer scale and the inner scale. They go in different directions. But the outer scale always has smaller markings, which is better if you want a more accurate angle measurement. But sometimes you don't need those because it's clearly on one of the lines that are drawn here. So you don't really need it. But usually it's better to use the outer scale. And even if you don't use the outer scale, you are going to have to convert it and do some calculations. So use a protractor to find the measure of each angle. So for the first one, we put the hole and then we measure it. And that would be, you usually put it an angle like this, around 40 degrees. Now, sometimes it's a tiny bit off the line, but it's also not to the next small marking, so you just have to round it slightly because there aren't markings for 0.2 of a degree, and you're probably wrong anyways because it might be 0.3 and it's way too small for you to tell. This one is 100 degrees, and now we move on to the next 2. This one is 70 degrees. And this one is, oh God, that is a weird number. All right, so it's 126 degrees. Yeah, sometimes it does this to you, and it gets super annoying because you're there wondering, well then, I have to make sure that you're 0.6. Well, no, not 0.6. You're 126 instead of 125 or 127. And because these lines are kind of thick, when there are thick lines, you, well, look for the middle of the line and measure that. Now, we are going to take a break from all the angles. Hooray, let's throw the protractor out the window. Actually, don't do that. Problem-solving strategy. Draw a diagram. Wow, doesn't this look familiar? Anyhow, Mark nailed a square piece of wood to a wall. That's a strange thing to do. Like, imagine just a normal wall, like a white wall, or whatever color your room walls are. Blue, yellow, red, pink, purple. But imagine just nailing a square piece of wood. Just wood. Okay, that's strange. But the wood measures 32 centimeters on each side. Mark puts a nail every 7 centimeters, including the corners. How many nails does Mark use? So step 1, understand the question. Read carefully. What do you know? So we know that wood is square. And side of square is equal to 35 centimeters. And nail, well, there is nail every 7 centimeters, including the corners. So what do you need to find? Well, how many nails are there that Mark uses? But we don't really need to write that. Just how many nails is fine. Since usually on a test or on anything you hand in, you don't actually write all of this down. This goes on in your head. So it's fine if you use jot notes, unless you're handing it in. Then you have to ask the teacher, is it okay if you use jot notes? So step 2, plan. Make a plan. And, well, step 3 is actually carrying out our plan. So for this one, we'll be teaching about drawing a diagram. Therefore, we will have to draw a diagram for our plan. So we can draw a square on graph paper. Now we carry out our plan in step 3, solve. Draw a diagram. The piece of wood is a square, so you should draw a square. Wow, rocket science. Okay then, I guess we have this sheet of graph paper. Now let's pretend every grid on the graph paper is 7 centimeters. So we start over here, let's pretend that's a corner of the square. And then that's 7, 14, 21, 28, and 35. That's another corner. And that would be 5 squares. So since it's a square, then the other side will also be 5 squares. So now we draw the square. And we draw where the nails would be. So there's the nails at the corners. And let's start on this corner. 1, 2, 3, 4, 5, 6, 7, 8. Oops. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 nails. Mark uses 20 nails. How many nails does Mark use? 20. Step 4, we check. Is the solution reasonable? Well, it's not unreasonable. Reread the problem. Well, let's go up and reread the problem. Mark nails a square piece of wood to a wall. The wood measures 35 centimeters. We got that. On each side. Well, we got that too. Mark puts a nail every 7 centimeters, including the corners. That's what we did. How many nails does Mark use? So we read it the right way. Have you answered the question? Yes. We answered how many nails does Mark use, which is the question. How can you check that your answer is reasonable? Well, we could use another solution. So think about it. Since, well, there's 4 sides, and we also do the corners, and each side is 35 centimeters, and a nail is in every 7 centimeters, then we could do 35 divided by 7 equals to 5, and then 5 times 4, because there's 4 sides, and that would also be 20. So we could use another strategy. So now we solve these problems using the draw a diagram strategy. A table is 6 feet wide and 8 feet long, so that there is a plate every 2 feet, except at the corners. How many plates are on the table? So we know that the table is 6 feet wide. Let's pretend that's 6 feet. And 8 feet long. Let's also pretend that's 8 feet. So that's a rectangle. And it's set so that there's a plate every 2 feet. So every 2 feet there's a plate, except at the corner. Because you never want to sit at a corner. It's pretty painful when you do that. How many plates are on the table? So then we draw the diagram. Let's pretend this is 8 feet and this is 6 feet. So we start at the corner, except we don't count the corner. And then we go 2 feet, 4 feet, 6 feet, 8 feet, and we don't put anything at this corner. So there's 3 plates on the 8 feet one. And it's probably the same thing on the other side. In fact, it is the same thing because it's the same measurement and it's, well, the same requirements. There's no plates at the corners. So 2 feet, 1, and then another 2 feet, that's 4, well, 2, 4. Then there's 6 after another 2 feet. So there's 2 plates on each of the 6-foot sides and 3 plates on each of the 8-foot sides. There's 2 6-foot sides, so 2 times 2 equals to 4. And then there's 2 8-foot sides too, so then 2 times 3 equals to 6. So 4 plus 6 is 10. There are 10 plates on the table. Hooray, we're done. So we check. Everything looks reasonable. We understood the problem properly. And the answer is sensible, so we're done that. Now, question number 2. To enclose means to, well, seal off, a garden that is 15 feet long and 12 feet wide, fence posts are set every 3 feet, including the corners. How many posts are needed to enclose the yard? So we could always use division like we did for the last one, but since we're supposed to draw a diagram, then we're going to do that. This is 12 feet, and this is 15 feet. Pretend that that's what Ashley is, because obviously I'm not going to draw 15 feet worth of stuff. So let's start at the corners. And there's a post there. So 12 feet would be 3, 6, 9, 12. So there'd be 5 there. But we don't count one of the corners because one of the corners belongs to another side. So now we start here. This is 15. So 3, 6, 9, 12, 15. And we keep going. But we realize that on the 15 side, there's 5 posts if you don't count a corner. And that would be 5. So 5 times 2 because there's 2 15 sides. It would be, well, 10 because 5 times 2 equals to 10. And then for the 12 feet, it would be 4 posts, and 4 times 2 equals to, well, 8. So then 10 plus 8 equals to 18. 18 posts are needed. You could write to enclose a yard, but I'm not going to. Now you may be wondering, why is it like this? Because, well, we can't count the corners twice. So everything will have to be counted in this sort of way. Yeah, it looks pretty weird. It also looks kind of like some logo designs. Anyhow, we're going to continue. Oh look, we're at section 3 now. Estimating and drawing angles. 1. To estimate the measure of an angle, use measures you already know, such as 45 degrees, 90 degrees, which is a right angle, and 180 degrees, which is a straight line. You can estimate the angle to be a bit smaller or larger than these measures. So which one is this closest to? Well, we know that it's not closest to a straight line. We also know that it's not really that close to what is around, okay, that's not 45. 45 is around here. 45, but it's pretty close to 90. But it's a bit bigger. So a good estimate would be for angle A, well, 100 degrees. What about B? Well, we realize that B is closer to 45, but it's a little smaller. So when you're doing angles, you usually go down or up, at least for estimating, in increments of 10. So let's just say that that's 35 degrees for angle B. That's a good estimate for angle B, right? Now, let's do some practice. Estimate the measure of each angle. So this one, it's larger than 45, but it's smaller than 90. And it looks slightly closer to 90 than 45. What would be a measure that's around the same amount to both, but slightly closer to 90? 70 degrees. Now this one, we can tell that there's a straight line down here as a reference, and it's not that close, but it's also not that close to 90 either. It actually looks around halfway. So what's 90 plus 45? Because 45 is halfway between 90 and 0, and 90 is halfway between 0 and 180. So 90 plus 45 equals to 135. So this angle is around that. Now this one is obviously smaller than 45, but it's not to the point of being 0. It also looks a little bit bigger than 10. So it'd be around maybe 15 or 20. Let's just put 20. Yay! We're done. Your estimates may be a little bit larger or bigger, but make sure that it's not drastically larger or bigger, because that would be not good. Now we learn a little more. Look at line AB and line CD. Are these lines parallel, perpendicular, or neither? So you have 3 answer choices. What's parallel? Parallel means that the 2 lines never intersect. Never. They're just together, going in the same direction, at the same rate. It's called slope. You learn that in later grades. And they never touch. So perpendicular is when 2 lines meet at a right angle, 90 degrees. So in order to determine whether or not the lines are parallel, perpendicular, or neither, we need to ask ourselves some questions. So do the lines cross or intersect at a point? Well, why yes, they do. Yes. So do the lines form a right angle? Well, right angles don't really look like that, so no. So since they intersect, we know that they're not parallel, since parallel lines never intersect. But they also don't form a right angle, so they're not perpendicular either. So they are neither. And we write a big fat neither right here. You could make it more eloquent and sound nicer, like say, lines A, B, and C, D are neither parallel nor perpendicular. But for this, I'm just going to write that. Use the figure to determine if each pair of lines is parallel, perpendicular, or neither. So first, we have line FE and CD. So FE is this one and CD is this one. Oh look, there's that little squarish thing. That little squarish thing means that it meets at a right angle. So they intersect and they meet at a right angle. So they're perpendicular. Okay, one thing, guys, perpendicular lines can never be parallel, because if they're perpendicular, then they meet, and parallel lines don't meet. Okay, now AB and KD. AB is here, and where's KD? Oh, KD is here. Oh, there's these little arrows that are not at the end of lines. So they're not continuation arrows. But if there's these little arrows, then that means that they are parallel. And they don't meet ever. So they're parallel. Now, HG and IB. HG is here and IB is here. HG and IB intersect at J, but they don't intersect at a right angle because we don't see this little squarish thing. So it's neither. Now we have HJ and EF. HJ is here and EF is here. So they intersect, so they're not parallel. Now you may be thinking that they're perpendicular because there's this little square, but no, that's not for those two lines. So they're not perpendicular either. So it's also neither. Now we have if, and AB. IF is here and AB is here. So IF and AB, they meet at I. So they're not parallel since they meet, but at I, there's this square. So they meet at a right angle. And therefore, they are perpendicular. Now, for our final question, we have AJ and CK. AJ is here, CK is here. So you may be thinking, I know that they don't meet, but I don't see that arrow thingy. Well, the arrow thingy, because this is a continuation of this line, is over here. So AJ and CK are essentially parallel. So we write down parallel. Yay, we're done that. So now we're at section 5. Problem solving investigation. Again, choose the best strategy. Which part of the pizza is larger? 3/8 of the pizza or 2/6 of the pizza? Well, the second pizza. This looks familiar. This looks like equivalent fractions. But since, well, you already have a diagram of the two pizzas, you might as well use them. So, first step, understand. Be sure you understand the problem. You need to compare two parts of pizzas and you need to see which one's larger. That's what the problem asks you. Now for our plan, we already have a diagram of the two, so we might as well use them. But, well, we could make those into decimals, make them into equivalent fractions. We could do many things actually. So carry out our plan. First, we're going to go with our first method, which is, well, seeing which one is larger. And it seems that 3/8 is larger by just a little bit. But we also have a different strategy, which is to change both fractions into decimals. So we can divide them, and 3 divided by 8 is equal to 0.375, and 2/6 is also 1/3, and 1/3 is 0.333 repeated. So instead of that, we could always write 0.3 and just write a line on top. When there's a line on top, it means that that digit or that bunch of digits is continuously repeated. Which one's bigger? 0.375. And that matches with our answer up there. We can also use equivalent fractions. So 3/8 is equal to, and 2/6 is equal to. So we can use the lowest common denominator, which is also a concept. and that would make it 24. Or we could guess and check for this. 8 over 24. This one would be 9 over 24. This one's still larger. Just like, well, all our previous results told us. So we're on the last step. Finally. Is the solution reasonable? Yes. Reread the problem. 3/8 of the first pizza or 2/6 of the second pizza? Which part of the pizza is larger? How can we check our answer? Well, we essentially just did. We did it 3 different ways. So we can use any strategy shown below to solve each problem. We can look for a pattern, we could draw a diagram, and we could guess and check. I don't like guess and check personally, but if you like it, then that's your personal preference. Which is more, 7/8 of an apple pie or 8/9 of the same pie? Well, let's convert them into decimals. We could always draw a diagram, but it's really inaccurate if you don't have the right tools. So instead of drawing a diagram, we're just going to do some good old-fashioned long division. Well, now we found out what 7/8 of the pie is. And we need to find out what 8/9 of the pie is. Let's do some calculations. Oh. This is a repeating decimal, okay. Oh, you actually don't need to write it that way. So 8/9 of a pie is 0.8 repeated. So 0.8 repeated is bigger than 8.75 because 0.888 is bigger than 0.75. So conclusion, 8/9 of the pie is more. Done. Now we move on to the next question. On Monday, Veronica had 20 minutes of homework. On Tuesday, she had 30 minutes. On Wednesday, she had 40 minutes. If the pattern continues, how much homework will she have on Friday? So we can't look for a pattern in this one because it is a pattern. So first day there's 20, then there's 30, then there's 40. So Monday, Tuesday, Wednesday, and then we have Thursday and Friday, which is 2 more days. So if we keep adding 10 minutes, then we add another 10 minutes, so that's Thursday. Thursday she will have 50 minutes, and then we add another. So that would be 60 minutes. Oh, okay, that's an hour. So since the problem asks in minutes, we should probably answer it in minutes too. So Veronica will have 60 minutes of homework. On Friday. All right. Now we have question number 9. Charo is 3 times as old as Lorena. In 5 years, Lorena will be half Charo's age. How old are Charo and Lorena now? So right now, Charo is, well, C, which is Charo, is 3 times as old as Lorena. So 3 times as old as Lorena. So in 5 years, Lorena will be half Charo's age. Then that means that Charo, who also ages 5 years, would be 2 times L plus 5. Yeah, this is more of an algebra question. You can't really guess and check because that would take way too long. And you can't really draw a diagram for it. You also can't really look for a pattern. So conclusion is C equals to 3 times L, and C plus 5 equals to 2L, or 2 times L, plus 10. So we can move that over there. That would be C equals to 2L plus 5, because in order to balance this, then plus 5 would have to, you would have to subtract 5, and then you have to subtract 5 from this side. So 3 times L equals to 2L plus 5. L equals to 5. Wow. Lorena is 5 years old. Okay, who thinks about this when they're 5? But okay. And since Lorena's 5-year-old and Charo is 3 times as old as Lorena, then Carl is it Charo or Carl? Carl is 15 years old. Okay, I really need to know if it's Carl or Charo. Come on, guys. Tell me the answer. So now we check. If in 5 years, Lorena will be half Charo's age, then in 5 years, Lorena will be 10 years old, and in 5 years, Charo will be 20 years old. 10 is half of 20. Okay, that works. Everything works, and our solution is, well, right. Justin has 6 shirts and 5 pairs of pants. Okay. If he wears a different combination each day, how many days will pass before he has to repeat a combination? Okay. We could always draw a tree diagram. And oh no, I don't have enough space for 6. Okay, 6. And then have 5 branches off of each. But that would become long and tedious and space consuming and messed up if you don't have enough space like I do now. So essentially it's just 6 times 5, which is 30. Oh, this man will actually last a month. So 30 days will pass. Congratulations, Justin. Now, an artist draws a circle, 2 lines, and a triangle. What shape will the artist draw next? I'm assuming there's supposed to be a pattern here. But this is one strange question. So a circle, 2 lines, and a triangle. So over here there's 1 stroke, I guess, and then 2 strokes, and then 3 strokes, or lines. So what has 4 strokes? Well, a quadrilateral. Quadrilateral is any shape that has 4 sides. Rectangles, squares, parallelograms, rhombuses, you name it. We are going to be learning about that a few sections later. Let's assume it's a square. The artist will draw a square next. Okay. If your teacher is picky, they might mark you wrong for it because they're going to tell you that he could have drawn a rectangle, or she. So the safer thing to write will be, we'll draw a four-sided shape or draw a quadrilateral. Well, I guess that's done. At a party, everyone shook hands with everyone exactly once. Oh, it's one of these type of questions. There were a total of 28 handshakes in the room. How many people were at the party? Okay, so these type of questions, it's addition. So think about it. If 3 people, then one person, and then since these two have already shaked hands, this person only needs to shake with this. So that would be 2 plus 1. But if there was another person, then it'd be a diagram that's like this. And then there's also this because, well, that happened. So that would be 3 plus 2 plus 1. And you keep going. How many people are in the party? So let's do this. 1 plus 2 equals to 3. Plus another 3 equals to 6. Plus 4 equals to 10. Plus 5 equals to 15. Plus 6 equals to 21. Plus 7 equals to 28. Okay. 7. Now you may be thinking, there's 7 people. No, there isn't. Because remember, when there was 3 people, then it's 2 plus 1. When it's 4 people, it's 3 plus 2 plus 1. And then when there's 5 people, it would be 4 plus 3 plus 2 plus 1. So if there's 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, then that would be 8 people. There were 8 people. Yay, we're done that. Now we're on section number 6, where we'll be teaching you about triangles. You can classify triangles by the length of their sides. So equilateral has 3 congruent sides, meaning that the 3 sides are all the same length. Equi stands for equivalent, which is equal, and lateral is, well, a side, a line, a side. So usually they would put marks like this to tell you that they're all equal. So isosceles triangles have at least 2 congruent sides. So at least 2 of the sides are, well, the same. Now you may be questioning, if it's at least, then are equilateral triangles isosceles triangles? Yes, they are. It's just more specific. It's like how squares can be rectangles, but not all rectangles are squares. Then there's scalene, and they just don't have any sides that are equal. So the markings would be something like this. If there's a different number of lines on the marking, then that means that they aren't, well, equal to something with a different number of lines. So if there's 2, 3 lines, then that means these 2 sides are equal. But there isn't. We can also classify triangles by the measures of their angles. So we have right triangles that can do no wrong. A. Where there's 1 right angle. It's impossible to have a triangle with 2 right angles because then it would look like this. And it wouldn't be a closed polygon. And triangles are closed polygons. And we can't do this either because then that'd be a square or a rectangle. Or something else. Acute? Oh look, acute triangle. I'm sure you've heard that joke somewhere. So there's 3 acute angles. And obtuse, there's, well, 1 obtuse angle. It's impossible to have 2 because then it'd be like this. No. Circle the characteristics of each triangle. Then classify the triangle as equilateral, isosceles, or scalene, and right, acute, or obtuse. So in this one, it looks like it's equilateral, or isosceles, because isosceles is at least 2 congruent sides. But there aren't any markings. Usually on a book there will be markings, and if there isn't, you should ask your teacher. Because sometimes they like to mess with ya. So there's 3 congruent sides. We circle that. and all of them are acute. So it would be equilateral acute. Alright guys, I need to tell you something really important. Equilateral triangles are never right. They're always wrong. Nor are they obtuse. They're always acute because when you have three congruent sides, the angles are also equivalent to each other, and the total angle measurement in a triangle would be 180 degrees, and 180 divided by 3 is, well, 60, and 60 is not equivalent to 90, which is a right angle. Anyhow, question number 2. This one. Okay then, nothing's congruent. Nothing, absolutely nothing is congruent. Well then. So no congruent sides, that's scalene. And there's no obtuse angles, no right angles, and there's 3 acute angles. So scalene acute, or acute scalene. Depends on what notation your teacher prefers. Anyhow, we're done that, and now we're finally on quadrilaterals, like I promised you. So you can classify quadrilaterals by their sides and angles, just like triangles. So parallelograms, opposite sides are congruent and opposite sides are parallel. So let me draw the parallel arrow thingies. And then the congruency. That's a parallelogram. A rectangle, opposite sides are congruent, opposite sides are parallel, and there's 4 right angles. So is a rectangle a parallelogram? Yes. Just like how squares can be rectangles, but rectangles are not always squares. So we can see the little boxy square right angle markings. Now squares. All sides are congruent and opposite sides are parallel, and there's 4 right angles. So if all sides are congruent, then are the opposite sides also congruent? Yes. So squares are also parallelograms. They're also technically rectangles. Rhombus. All sides are congruent, just like a square. And opposite sides are parallel. The only difference between that and a square is that a square has the 4 right angles. So are rhombuses parallelograms? Yes. It looks actually a lot like the parallelogram up there, just squished. And then there's the trapezoids. There's also the kites, but we don't really teach you about that in this grade. So trapezoids have exactly 1 pair of parallel sides. This one and this one. These 2 are never parallel. They may be equal though, and if they're equal, then it's called an isosceles trapezoid. And if there's a right angle, say like here, it would be a right trapezoid, because all other trapezoids are wrong, apparently. Now, here's a practice. Circle the characteristics of each quadrilateral. Then classify the quadrilateral in as many ways as possible. Okay. There's not any, well, those square thingies, but these are right angles. So you might want to clarify with your teachers, any of your math teachers, if they marked the things or not, because in a book it usually would. So the opposite sides are congruent. Not all sides are congruent. The opposite sides are parallel. And there's, well, not 1 pair of parallel sides, there's 2 because the opposite sides are parallel. And there's 4 right angles. So it's not a square, but it is a rectangle. And rectangles are also always parallelograms. So it's a rectangle, that's also a parallelogram. But usually you would just call this rectangle. Now this one. Opposite sides are congruent? No. Are all sides congruent? No. Are opposite sides parallel? Does this look parallel? No. How many pairs of parallel sides are there? Well, one. So there's exactly one pair of parallel sides, yes. Are there 4 right angles? No. There's 2 though. And that's what you would call a right trapezoid. So we're on section 8 now. The last section. Feel free to take a break in any part of the video if you want to have a drink of water, go to the bathroom, do some practice questions, but we're gonna start section 8 now. So, drawing 3-dimensional figures. Ooh, nice. So look at this figure. Take a close and careful look at it. Stare at it. Stare into its essence and soul. Are we done? Okay. Can you draw the top, front, and side view of this figure? Well, first we're going to start with the top. So we usually would shade in what we can see of the top. And then we draw it flat. Because when we draw views, we always draw views flat. Oh, that's not the best I've done. And then these are the 2 sides over here. And then there's the 3 squares in the middle. They aren't exactly squares. This isn't perfect. Draw it with a ruler when you are at home. So to do a top view, you would imagine that you are a bird, or you're on a plane, or something like that. Or you just have the figure on the floor and you're just looking at it from above. You just need to remember that you are looking at it from above. So now you pretend that you are standing from the side, which are the 2 bits that aren't facing you. The front and the side are very different. The front is the one actually facing you, and they're different views too. So that's called the top view. So this is a side view now. So we shaded in the side. So the side view is actually pretty boring for this one. That's it. So now we're trying to find the front view. We shade in the front. And oh, this is also pretty boring. There's 2 squares high and 5 squares wide, so yeah, try it with a ruler when you're at home. Now we draw a top view, a side view, and a front view of each of these 2 figures. So when we're looking at this from the top, what do we see? We don't see this thing protruding out. We just see a flat grid, and it's 3 grids wide and 3 grids long. So, oh, that looks like a frame picture of a tic-tac-toe grid. Okay, that's pretty strange if anybody frames tic-tac-toe grids. I mean, if it was a really nice victory, anyhow, let's keep moving on. So the side view, you would shade in the side, but from the side you would still see this thing that is poking out. So the side view would still look like so, since there's, well, there's 3 over here and there's 3 over here, but the side view would have this thing on top sticking out. So with the front view, because the front view and the side view for this figure looks the same. So when you're actually doing these problems, please label. Now this would be top, side. Oh, that looks delta. And front. Alright, so how about this one? When we look at it from the top, we don't see these things sticking out. We just see, well, a straight line. So the top view would be, it's 5 squares long, right? 5. Something like this. Top. Now the side view. The side view, we also can't really see this nook over here. So all we see is something that is 3 squares tall. Side. Now the front view. The front view is interesting because we can see all of these. So the front view would be, that's 5 squares. And then it's 2 squares over here. Then there's 1 square over here. Front. Yeah. Now we're done. That's it. Remember to do the practice problems at home.